and welcome to the first week of the course Calculus 1 from functions to differential equations. Since this is the beginning of the course, we know the topic at hand, functions. Functions are fundamental to how we put mathematics into practice via models. The definition is very simple. A function f associates exactly one real number f of x to any real number x in the domain D. We call the number f of x the output value associated to the input value x. Another name for output value is function value, and another name for input value is value of the variable. The domain D is just all the possible input values and shall be discussed later on. Functions are very versatile. For instance, we may interpret the input values as times and output values as a corresponding quantity at that time. To make it specific, we could consider the function h that associates to each value t the height of some object t seconds after dropping it from some height in a vacuum. The input values could also be something completely different, however. For instance, we could consider p to be the function that associates to each value t the pressure of some fixed volume of ideal gas at T Kelvin. In order to analyze and thus use functions, we will need to express them in a convenient way. It will not do to list all possible input values with their corresponding output values. The best way to express a function is by using a formula. This tells us the value of f of x in terms of some operations performed on x. For example, in the case of the falling object, we find that h of t equals h minus 1/2 times g squared times g times d squared, where g is a gravitational constant and h is the starting height. For the ideal gas, we find that P of t equals n times r times t divided by v. Here v is the volume of the gas, r is the gas constant, and n is the amount of molecules in the gas. Note that we are treating only the temperature T as a variable, and all the other quantities in the formula are simply constant. They are fixed numbers. A formula gives the entire function, since in order to figure out the value associated to the input value x, we simply perform the operations to obtain the output value. For instance, for the falling object, if the initial height was 200 meters, and we find that g is equal to 10 meters per second squared, we find that at time t equal to 5 seconds, the object is at height 200 minus 1/2 times 10 times 5 squared, which equals 75 meters. We can find the height at some other time just as easily. For instance, the height at time t equals 3 seconds is equal to 200 minus 1/2 times 10 times 3 squared, which equals 155 meters. We will use functions many times throughout the course. It can be hard to get a good idea of a function just from a formula. Since a picture says more than 1,000 words, we should consider a visual representation of a function in order to gain a lot of information about it at a glance. We find this in the graph of the function. The graph of a function is given by drawing a curve through the points with coordinates x and f of x in the plane. For example, here we have the graph of the falling object function, and here we have the graph of the pressure of an ideal gas, where we consider the constants to have the values v equals 1, n equals 45, and r equals 8. Note that we can find the value assigned to a value on the x-axis by drawing a vertical line at that x value and seeing where it crosses the graph. The y-coordinate of the point where the line and the graph cross is the output value, corresponding to the input value x. This also answers an interesting question for us. Namely, suppose I simply show you a picture of a curve in the plane, then is it possible to determine whether this is the graph of a function? Indeed, it is possible, and we call the method by which we do it the vertical line test. A function should give exactly one output value for each input value in the domain. So a curve is only the graph of a function if every vertical line at an x value in the domain intersects the curve in exactly one point. Consider, for example, the curve shown on the slide. This curve is not a graph of a function on the domain ranging from x equal to minus 1 to x equal to 1, since the vertical line at x equal to 0 does not intersect the curve at all. If we leave the value x equal to 0 out of the domain, it is the graph of a function on that domain. How about this curve? This is also not the graph of any function on the domain D ranging from x equals -1 to x equals 1, since the vertical line at x equals 0 crosses the curve in more than one point. If we look at the examples of functions we saw earlier, we do indeed see that the graph of those functions intersects exactly once with any vertical lines in their respective domains, as you can see on the slide for the example of the falling object.